You found the skeleton. How would you tell it's a dinosaur? You personally, how would you decide?
Well, interesting question. I don't know. I'd have to do some research on that.
Hey there, YouTube. The Dapper Dinosaur here. We left off with Myers telling us about the theoretical work on the so-called waiting time problem, and I was explaining why, in fact, that is not a problem. Steve is now going to cover more of the same, but it's going to be more math-heavy. So, here we go.
And as those calculations are being made, if you get beyond 2 or 3 coordinated mutations, the waiting times just balloon well beyond the time available for the entire history of life on Earth, excepting the great ages that most geologists talk about. So,
weird then how we know of actual mutations which required more coordinated mutations than that have happened in laboratories in decades. Not, trillions of years. Like the CIT+ line of Escherichia coli bacteria in the Lenski long-term evolution experiment. I guess that sucks then. So we know both from theoretical work that creationists are using the wrong math with the wrong assumptions, and we know from a practical standpoint that it just doesn't take that long, because we can watch it happen.
Give them 3.5 billion years. It's not enough time to generate the kind of changes that we see in the history of life using the mutation natural selection mechanism. So that's a big problem.
No.
Now, in my book, I discuss this problem in light of another discovery that makes the problem even more acute. And that is the discovery of the information-bearing properties of the DNA molecule. This discovery came in the 1950s. Watson and Crick, I'm not pressing the right buttons up here, thank you. Watson and Crick elucidate the structure of DNA in 1953. The structure, they realized right from the beginning, suggests that the DNA molecule may have the capacity to store information in a digital form. In 1957, Francis Crick proposes something called the sequence hypothesis, in which he suggests that the chemical subunits along the interior of the DNA molecule are functioning like alphabetic characters in a written language or digital characters in a section of machine code, the zeros and ones in a section of software. Which is to say, it's not the chemical properties of these chemical subunits in DNA that matter. It's not the shape of those subunits. It's their arrangement in accord with a symbol convention or code that allow them to convey instructions for building all the important proteins and protein parts that cells have that keep them alive. I'm competing with myself here. Okay.
I let that go for a long time because, well, nothing he's saying is news to evolutionary biologists or population geneticists. Just explaining how an aspect of modern biology works isn't exactly a slam dunk against modern biology.
So I've got a little piece of animation that I'll just run in the background as I'm describing this, but this has been one of the great discoveries of modern biology. It's a stop-press moment in the history of life. The biologists discover that code is literally running the show inside living systems.
Yeah, so?
Let me give you an analogy.
Who wants to bet it's a bad analogy to some human-made thing that doesn't have the important properties of life, like replication with variation?
And as you can see some of the animation running in the background, it's explaining how, and you can watch this on my website if you're really interested tonight, the animation is explaining how the digital information in the DNA molecule directs the construction of the protein parts that are so important to keep our cells alive. Proteins perform all the important jobs. They catalyze reactions. They form the structural parts of molecular machines. We have inside cells extraordinary little tiny nanomachines, rotary engines, sliding clamps, turbines. It's just extraordinary. They're typically made of proteins, and the proteins also process information.
Holy crap, dude, get to a point.
So you've got this extraordinary process going on inside the cell, and here's the analogy. Any engineers here in the audience?
Of course there are. The Salem hypothesis strikes again. For those of you who don't know, the Salem hypothesis says that engineers are more likely to become anti-evolutionists because they already tend to see things in terms of intentional design. Because that's the whole point of an engineer, to intentionally design systems.
Okay, some engineers. Familiar with CAD/CAM, computer-assisted design and engineering? I'm from Seattle. We've got two really famous companies up there, Microsoft, where they write code, Boeing, where they use code to direct the construction of mechanical systems called airplanes.
Well, I guess I won that bet. If it doesn't reproduce with variations in heritability, then it's a bad analogy for evolution. In fact, really, you should try to explain a point before making an analogy in evolution, because analogies are actually mostly pretty bad, and you can't rely on them to teach ideas in biology.
So you've got an engineer sitting at a console. He writes code to specs for producing a particular part. That code is sent down a wire. It's translated into a machine language that can be read at the manufacturing center, and then that manufacturing center will take that information and use it to, say, place rivets on exactly the right place in the airplane wing. So you build the airplane wing according to specs. Information directing the construction of mechanical systems. That's what's going on inside cells. Molecular machines made of proteins. The proteins are built according to the specs, the instructions stored in the DNA molecule. It's a mind-blowing discovery. Now, I call this discovery the DNA Enigma.
Of course he does, because it's not at all enigmatic, and because that makes it seem like scientists are just scratching their bums not being able to figure out anything about how evolution could possibly work.
And the enigma here is not, it's not, sorry, let's go, yeah, there we go. It's not what the DNA does. It's not even the structure of the DNA molecule. Watson and Crick solved that for us. The information is, the enigma is, where did the information come from?
From mutations, which literally change the information in DNA. If the information is a sequence of nucleotides, which it is, and mutations are what we call changes in that sequence, which they are, then problem solved.
Okay. And I found in talking to students, nobody talks about that in biology classes. They just say, here's what DNA is, here's the structure, here's what it does, but no one raises this deeper question, where did it come from?
I'm going to need a citation for the idea that no one in biology classrooms talks about mutation. That's not been my experience in biology classrooms. Also, I asked Dr. Dan Sturden-Cardinal if he mentions mutations. Oddly enough, it turns out that he does, and he teaches these subjects.
Now, I also used to ask my students the question, if you want to give your computer a new function, what do you have to give it?
Nope, we're not allowing intentionally misleading analogies. We're skipping all this dumb shit about computers until he gets back to biology. Computers do not work like cells. Sorry.
If you want to build a trilobite from whatever simpler form of life was around before, you've got to generate a whole new group of specialized cells. Every new cell type needs dedicated proteins.
Good thing we have seen new proteins develop in historical times, and that we know what mutations have occurred to get them.
If you're a gut cell, for example, if you have a gut in an animal, those cells need enzymes, digestive enzymes to do their job. And those proteins are constructed in accord with the instructions stored on that DNA molecule. So what's this all got to do with the Cambrian explosion?
Presumably that it happened a bunch at the time, which isn't surprising in one of the biggest adaptive radiations in the history of life on Earth.
Well, when we see all these new forms of animal life, we're not just looking at an explosion of new form, of biological form, we're looking at an explosion of new information.
Good thing we already know where information in the genome comes from then. In fact, just the idea that Meyer thinks the waiting time problem is relevant to this discussion means that he too thinks that, at least in principle, mutation can create information. He just thinks it happens too slowly. Since we already know he's dead wrong about that, this problem is solved. Basically, his whole enigma is, well, mutation isn't fast enough, so maybe God created new genetic material. Except, it is fast enough. And now he's couching the whole thing in terms more familiar to most people from computing, or perhaps book printing, areas that are not analogous to living organisms and which demonstrably both require and have design. This makes it seem like living things also need design. The whole thing is a dishonesty built on top of a pile of faulty assumptions that then use wrong math. Pro tip, if you're going to try to overturn all of biology, you might want to actually get it right first.
And that's the big question that my book addresses. Where does that information come from?
If this talk is any indication of how good a job he does addressing this question in his book, then Stephen Meyer owes a personal apology to each and every one of the 3 trillion or so trees that exist for crimes against their cousins that he committed in having them felled to make the paper his book was printed on.
Now, there's a couple of, there are many reasons that the neo-Darwinian mechanism, the idea of natural selection acting on random mutations.
We wouldn't want to muddy the water with sexual selection, drift, neutral theory, niche partitioning, etc. Just natural selection and mutation, that's it. The last 160 years of evolutionary biology didn't happen. Seriously, I wonder if Meyer could pass a freshman intro to evolutionary biology course final exam. I doubt it.
Does not explain the origin of that information.
It does, in the word mutation. After that, there's another software analogy.
We don't do that here.
There's a big mathematical problem with the idea that random changes can generate new information. The problem is there's a reason that the random changes tend to degrade information, and that is that there's a lot more ways to arrange characters in any system of any combinatorial system for conveying information. There's a lot more ways, a lot more arrangements that will produce gibberish than there are that will produce meaningful text or functional sequences.
Yeah, but how much more? And how does this apply to DNA? Well, the first thing we can look at is, are there mutations that do nothing? Let's go over genetics 101, like high school level genetics. Now, this is profoundly simplified, but these basics are needed for this discussion. A gene is a unit of DNA that codes for a protein, and it takes the form of a series of codons, starting with a start codon and ending with a stop codon. Each codon consists of 3 nucleotide base pairs. Since only one side of the DNA is read, we can simply use the nucleotide on the side being read, either uracil for RNA or thymine for DNA, then adenine, cytosine, and guanine. Proteins are made of strings of amino acid, and the codons, other than start and stop codons, code for amino acids which are added to a building protein molecule in sequence. Well, in DNA, we have 64 possible codons. Now, of those, we have 2 codons for phenylalanine, 6 for leucine, 3 for isoleucine, 4 for valine, 6 for serine, 4 for proline, 4 for threonine, 4 for alanine, 2 for tyrosine, 2 for histidine, 2 for glutamine, 2 for asparagine, 2 for lysine, 2 for aspartic acid, 2 for glutamic acid, 2 for cysteine, 1 for tryptophan, 6 for arginine, 4 for glycine, 3 for stop, and 1 for start. So already we can see that we only have 21 things a codon can code for, and the only codons that are actually unique are the start codon and the tryptophan codon. So we can already see that a large portion of mutations are actually going to end up being between codons that do the same thing, called synonymous codons. Mutations of this kind have literally no effect on the protein produced. Further, much of DNA exists between genes as simply spacer, and the important thing about that DNA is not its sequence, but that it simply exists, so genes don't run together. This DNA is not what is called sequence-constrained. Sequence-constrained means that the sequence of the DNA is important to the organism and so is subject to selection. Non-sequence-constrained DNA can withstand virtually any mutation other than huge deletions, and the organism can essentially be unaffected. Now, genes are generally sequence-constrained, and so are regulatory regions such as promoters. Now, it's not really worth it to go into detail about exactly how promoter regions work, but they receive chemical signals, and then this activates the genes they promote to create the proteins in question. The structure of promoter regions and genes associated with them is common across life, although bacteria arrange these things very differently. In bacteria, their genes are grouped into what are called operons. An operon contains a set of related genes that all have to do with a single function, such as all the proteins needed to metabolize a particular food source. So if Meyer is right that sequences that do nothing are vastly more likely than those that do something, if we were to take an operon promoter from a bacterium, which happens to be about 100 base pairs long, and replace it with, say, absolute random noise, we should expect virtually no activity of the operon, since that random noise shouldn't be able to produce functional promoters. Well, E. coli bacteria have an operon for digesting lactose, the sugar most common in mammal milk. Now, let's forget the fact that Meyer thinks that bacteria far predate animals, never mind mammals, and there would be no easy way to explain the existence of a lac operon at all when milk evolved billions of years later, according to him, which means that presumably lactose digestive enzymes would also have had to evolve, even though that's apparently impossible, according to him. We're going to forget that. So the operon, like all operons, has a promoter region. And sometime around 2018, a trio of scientists, namely Abihu Agiona, Eric J. Alm, and Jeff Gore, decided to do exactly what I was talking about. They replaced the whole promoter region with random noise in a bunch of bacteria, each getting its own unique bit of random noise. So if Meyer is right, basically none of them should be able to digest lactose. But 10% could, without any mutations, from random noise, some even better than wild type. So out of the 1.6 times 10 to the 60th power possible combinations of 100 base pairs, about 1.6 times 10 to the 59th power are functional as lac operon promoters. And of those random sequences, about 60%, over half of the random sequences, could function as lac operon promoters with only 1 point mutation. When Myers tells you that mutation can't provide function because there are so many ways for DNA to do nothing and so few ways for it to do something useful, he is ignoring that there are so many ways for it to do a given function that if we allow for one mutation, they fill up a significant portion of the sequence space available. If totally random noise can do that, then it should be no wonder that when starting with already well-ordered genes with specific functions, random mutations can and do provide new functions fairly easily, and without any particular need for a divine hand.
Just quick illustration. Turns out this is a bizarre thing, but if you take just a 12-letter word in the English language,
which has far more than 4 letters, arranged into morphemes that are often far more than 3 letters long, so, bad analogies for codons, and the majority of letter combinations do not form morphemes, so again, this is a bad analogy for codons, and I suspect an intentionally bad one. We already know that this is a bad analogy for DNA from the experiment we just talked about. We're still not doing analogies that don't apply.
Here's a familiar combinatorial system. It's called a bike lock, okay? It's got 4 dials, and each dial has 10 digits on it. So how many different ways are there to arrange the characters on the lock? 40, right? 10 plus 10 plus 10? What? Trick question, right? Okay. It's 10 times 10 times 10 times 10. There's 10,000 possibilities.
Thanks for the high school math problem, Steve.
Which is why a bike lock works, okay? If you imagine we've got a thief out there outside the school, sees a nice new bicycle that he'd very much like to have, but he encounters an impediment to his avarice, the lock, okay? Question, if he encounters a lock with 4 dials like this, is it more likely that he'll succeed in opening the lock or that he will fail to open the lock? Another trick question. Okay, our intuition is, fail, because we're thinking he probably isn't going to stay at this very long, right? But it does depend, can you see it does depend on how much time he has? I've made some stupid calculations that show if every 10 seconds you get 1 new combination, it will take you about 15 hours to search more than 5,000.
But let's compare this to DNA and use the actual experimental evidence of about 10% functionality. And just to be nice, we'll pretend that the 60% of sequences that are 1 mutation away from function don't exist. Now the thief only has to check 500 sequences to get to that 50% chance of unlocking the bike. So he now has a 50% chance of getting it in 1 hour, 23 minutes, 20 seconds, trying 1 combination every 10 seconds. Now let's say that he's not the only one trying. There are 1 million people trying to unlock the identical locks. This is to represent a very small population, since this is an analogy to evolution here, and that's a population level phenomenon. Well, now we're virtually guaranteed to get it on the first try, and the average length of time it will take to get the right answer is 5 milliseconds. Or, 10 seconds, since that's our minimum time. Funny how this doesn't seem like a big barrier anymore.
Once you get to 5,001, it becomes more likely than not that you'll succeed than it is that you will fail. So if we grant that our thief has 15 hours, then the answer to the question is, it is more likely that a random search will eventually generate the combination and he'll be able to open the lock. All right.
Yup, and it becomes trivial when you make assumptions more analogous to DNA.
But what if our thief, this is our thief out there, randomly searching, but what if instead of a 4-dial lock, he encounters one like this? Okay. Oh, thank you. That's the random search. And here's now the other lock he encounters. Okay. Now what? What's the situation now?
Well, let's say we have 10 billion combinations, of which 1 billion or so should work, so we have to search 9 billion combinations with that same population of 1 million or so. So that means that every 10 seconds we search 1 million combinations, and we need to search 4.5 billion combinations to have a 50-50% chance at solving the lock. Now, I know this isn't actually how you do this math problem. Stick with me, because in this section I'm being extremely nice to the point of doing math wrong in Meyer's favor. I'm going to here pretend that it actually matters how big the length of the sequence is, which would be true only if 1 sequence worked. But since that's not the case in DNA, it actually only matters what the functional fraction of possible sequences in the sequence space of that length is. For example, if 1 in every 10 sequences of any given length are actually viable, then to have a 50-50 chance of getting a viable solution, you actually only have to try 5 times no matter how long the sequence is. But we're going to set that aside and just continue to say the sequence length is the important thing. So if we search for a functional combination using Meyer's stupid math from 9 billion functional sequences, that means we need 4.5 cycles or 45 seconds to unlock the lock. I'm not seeing the problem here. And now you might say, but the problem of variable sequences is probably lower for sequences above 100 base pairs. Okay, sure. Let's drop it down a couple orders of magnitude. We're still at an hour and 50 minutes to get a viable solution. Again, using Meyer's stupid math. We're actually at basically 50 seconds, so it doesn't really matter. But still, even with his stupid math, an hour and 15 minutes. Now, we could get way more complicated than this and look into the chances that different people on different random walks encounter the same random sequence and whatnot, but I think you see my point. DNA doesn't have a single functional sequence, it has many, and we are trying many times to get the right answer. So it really isn't that big of a deal.
Is it more likely that the thief will generate the information he needs to open the lock in the time available to him? Well, let's give him his whole life. Now, I've made calculations on this as well, and it turns out that if he lives 100 years and does nothing but sample combinations, he's only going to sample about 3% of the total, okay?
So he's got a 30% chance or so of getting it right. But let's be nice again and toss away a couple orders of magnitude and say he's got a 3 out of 1,000 chance. So yeah, he's probably not going to get it. But there are a lot more than 1,000 thieves out there, so chances that someone gets it are pretty good.
So this is, first of all, a bad way to spend a life. And secondly, it becomes, can you see that in this case, with all the time available, it's going to be overwhelmingly more likely that he will fail than it is that he will succeed.
Any given individual, yes. But evolution happens to populations. We're not waiting for a single individual in particular to have a particular mutation. We're waiting for any of them in a large population to have any of a large number of possible functional mutations. That's going to drop the problem down, as we've seen, to basically no problem at all.
Which means if you're a betting person and you form a hypothesis about what's the likely outcome of such a random search, the hypothesis that he will succeed is overwhelmingly more likely to be false than true.
Okay, but what if I bet that someone will succeed, and I have a lot of people doing this, and about 0.1% of combinations work? Well, then suddenly it's a great bet. Now, of course, in all of this, we're still ignoring the fact that if any percent of possible combinations work, then really the correct way to calculate this is half as many attempts out of 100. So if 10% work, it really only takes 5 tries on average. And if only 0.1% work, then it only takes 500 tries. You can see how I'm being absurdly generous and it still doesn't cause a problem. That means that no matter how big the lock is, what matters is what percentage of combinations will unlock the lock. And we know it's more than just one combination. In fact, we know it's a lot more. His entire shtick depends on there being only one person making these combinations and only one of them being right. Both are stupid assumptions.
Can you see that? There's a connection to the truth or falsity of the chance hypothesis. Now, the question that I pose in the book is this. If we think of a gene or a protein as a combinatorial system, remember that picture of the DNA molecule that I had up there and had all the A's, G's, and T's? Well, you can see that there'd be a whole bunch of different ways of combining those A's, G's, and T's. And those are going to correspond to a whole bunch of different ways of combining what are called amino acids, which make up they're the subunits of the proteins that the DNA codes for. So what you're dealing with in biology are actually combinatorial systems.
But as we've seen, all 64 codons have meaning, so we're probably looking at a much higher than 0.1% of sequences having some function. See, that's the disanalogy with bike locks. The point of a bike lock is that only one combination works. Honestly, his analogy is just as dumb as the computer code, but I wanted to say that the minute you make even remotely realistic assumptions, no matter how you do the math, the dumb way or the real way, it just doesn't work the way Meyer wants it to. And yes, I intentionally sat down and did math wrong just to be generous to him and keep with his assumption that sequence length and not fraction of sequences that are functional was the important metric.
There's lots of different ways to arrange the characters in the DNA, only a very few of which are going to yield a functional protein.
But what proportion is that, Steve? He won't tell us because he knows it's a lot more than one. In fact, many combinations can result in the same proteins, and for any one function, more than one protein can do the job. That's why different organisms use different proteins for the same function. So this whole bike lock thing is stupid, and I suspect Meyer knows it.
And the question is, in the case of life, is it more like the first case, where with enough time, the thief could conceivably open the lock, where he'd get to a better than 50-50 chance of doing so? Or is it more like the second case with a 10-dial lock?
Well, since both cases are essentially the same, and we know that if you make it even somewhat analogous to actual life, both problems are completely trivial, I'd say that we have a nearly 100% chance that life can stumble on functional proteins with a random walk.
And I simplify here, and there's a lot about this in my book, but here's the situation mathematically. That's the search of our... if we're looking at just one gene with the information for building one new protein...
And remember, there is more than one gene sequence that can build a single protein, and more than one protein that can do a particular job.
The ratio of the sequences that will produce a functional protein to all the gibberish sequences is about 1 over 10 to the 77th power. This has been experimentally determined.
Really? Because actual experiments in random DNA noise seem to get more like 1 over 10. Weird. It looks to me like he's calculated the chance of a string of DNA getting a particular sequence of a given length, even though more than one of such strings can perform that function. Seems Steve here doesn't know what to put into his numerator. Oopsie.
For a very short gene and protein sequence. Okay? Now,
again, the length of the sequence isn't the important part. It's the fraction of such sequences that give a viable sequence. And it's more than 1 over sequence length. Now, I'll grant you that longer sequences would probably have lower proportions of functional sequences, but it's never going to simply be 1 over sequence length as the fraction of sequences that are functional.
There's only 10 to the 65th atoms in the entire galaxy.
Oh, we're doing the big numbers thing. Now, we're going to skip that. No matter how big you make your number that you made up to pretend that evolution doesn't work, it won't be a problem for evolution.
All right, so this is a big space to search, a big haystack looking for one little needle, okay?
But Steve, you know it's not one needle, don't you? And of course, you know that some of those bits you're searching in are needles for other function, and that the subset of functions an organism has managed to acquire versus the number of possible functions it could hit on is never going to just be 1. It's always going to be less than that.
But it turns out that there's only 10 to the 40th organisms in the entire, we're searching our 10 to the 77 possibilities. It turns out that 3.5 billion years is not nearly enough time to search this effectively.
Well, let's see. 10 to the 40th organisms, but that's that have ever lived, I presume. Let's be more reasonable and say it's 1 billion across the whole planet. And let's say that this is an important sequence that we really need in organisms, so we only have like 1 million years. And we're trying a combination per second. So there are 31,557,600 seconds in a year, roughly. That would mean that we're getting 31,557,600 billion attempts per year, which also means that over 1 million years, we're doing 31,557,600 attempts, or 3.16 times 10 to the 23rd power. Now, that's assuming only 1 billion organisms. That's probably not true. It's probably much closer to a very high number, but we're being generous, remember. Now, that's still way less than the 10 to the 77th power, but we already know that that number is nonsense from the Lac-Operon experiment. So what we have, really, is that with these fairly conservative numbers, we have a reasonable chance of stumbling across a protein if the actual fraction of function is somewhere around 1 in 10 to the 24th power. And the thing is, we have good reason to think that it might be well closer to 1 in 10 to the 1st. You know, based on that experiment that I bothered to cite, unlike this mysterious experiment of Meyer's. Now, I probably think it's not actually that high for most long strings of DNA, but it's not going to be as low as 1 in 10 to the 24th. You have to get to about 42 base pairs to even have so many options that only one of them being viable would get you to a fraction as low as 1 in 10 to the 24th. Also, curiously, 128 base pairs gives you a chance of stumbling across any particular base pair sequence of about 1 in 10 to the 77th. So I know that Meyer here is known to be factually inaccurate about nearly everything, and that he didn't bother to cite which experiment gave him these numbers, and that he didn't bother to cite which experiment gave him these numbers that he says are experimentally determined. But anytime I see a power of 2 raised to a power of 2, I get suspicious. It's the kind of thing you do to make your experiment easy for a computer to run the math on, not the kind of thing you usually get just running an experiment. I think that the experiment that determined this was that of a mathematician and not one that actually involved DNA of actual organisms. So, Dapper from the future here, I thought this was so suspicious that I asked my science friends about it. Turns out I was mostly right. The number of 10 to the 77th power comes from Douglas Axe, another Discovery Institute fraud. I was wrong that he's a mathematician, but right that it was just a mathematical thought experiment. He assumed that, given a functional sequence, any change to the amino acid sequence would remove that function. And so his number isn't even pretending to be the chances of finding a sequence with function. But the problem is that it also isn't the case that only one sequence of a given length can perform a specific function. Now, he was using amino acid sequences and not nucleotide sequences, but it works out the same way either way, so that's irrelevant. So since I'm on sort of a hemoglobin kick while I'm writing this, if Axe is correct, then when I look for natural variation in hemoglobin in humans, there should be literally 0. Instead, when looking on Google Scholar, the first paper I had reported over 1,000 known variants in humans. I'm sure some of these are less effective than others, but they're all transporting oxygen. So Meyer is misrepresenting Axe's work, which itself is already known to be false, by the simple observation of the fact that protein families exist with variable amino acid sequences, which all do the same function.
Because there's only been 10 to the 40th organisms in the whole history of life on Earth, which means that if every organism in the entire history of life, every time it replicated itself, was generating a new sequence of DNA, you'd still only search 1 10 trillion trillionth of the possibilities.
Yeah, if we took his word for it that the very suspicious number that was determined by some experiment somewhere by someone using some unknown method is a valid number, I have no reason to do that, and some good reasons not to.
Okay, 1 10 trillion. Yeah, that's right. Which means it's overwhelmingly more likely that a search for a new gene, that's a new stretch of genetic information, randomly like that, it's overwhelmingly more likely that such a search will fail than it will succeed, which means that the hypothesis that such a search did succeed is overwhelmingly more likely to be false than true.
A priori, that does seem to be the case. But then, biologists checked. Turns out that a very high fraction of random sequences have function, and more than half are within one mutation of having function. So, seems like we're doing pretty well on this front. And remember, a new functional sequence doesn't have to start out functioning very well. Once it functions at all, natural selection can take over to refine that function. So it's not like to get oxygen transport for some little worm, we need the full complexity of human hemoglobin. Any old protein that transports oxygen better than just diffusion is a boost to that worm's metabolism.
Which means that the neo-Darwinian mechanism is not a plausible means of generating new genetic information. Are people following roughly? Okay, kind of liken this to the 2 bike lock cases. This is like the 10 dial lock.
Again, we get the bad analogy. That implies there is only ever one combination that will work, when we know for sure that's not how DNA works.
And we're giving the evolutionary process essentially its whole life to look, the whole history of life on Earth. And it's not enough time to search the spaces, and so it's going to be more likely than not. Now, anyone seen this film? I think it was called Dumb and Dumber. It had a comic called Jim Carrey. He's kind of a goofy guy, and he sees across the room a lady that he fancies. And so he goes up to her, and he kind of goes, and he has a pickup line, and he says, what are the odds that a girl like me and a guy like you could get together? And he botches his pickup line right from the beginning, because he's actually the guy, And she says, not good.
Yeah, it's the 1 in a million line. Later, when he learns she's married, he asks, what was all that 1 in a million talk? Haha, we get it. Moving on.
Just because there's a finite probability of something having happened doesn't mean it happened that way.
That's true.
What you need to know is how many opportunities were there for that thing to happen, so you can make an assessment of the kind I just made to determine whether the chance hypothesis is more likely to have been false than true.
Yes, it is important to note that at a basic level, what he's doing is reasonable. If something is supposed to have happened in a stochastic manner, then if you can figure the odds, it's a decent way to see if the idea is plausible. But implausible things happen all the time. For example, a woman in 2009 managed to roll 154 consecutive rolls of 2 6-sided dice without rolling a 7. That has a probability of less than 1 in 10 to the 12th. Now, here's a link to a discussion about humans doing improbable things from a much bigger YouTube channel. Also, it's about Minecraft, so, lots of people like Minecraft. Now, if you found another person claiming to have done the same thing, say 1,000 times, that is so unlikely that it would be unreasonable to believe the claim. So while trying to figure out prior possibilities is a valid thing to do in some cases, when you start with nonsense numbers like Meyer does, well, you get nonsense conclusions. But that's where we're going to leave it for now. When we pick up, we're going to start moving a little bit away from all the math-heavy stuff, which will be nice for me, because while I'm okay at math, I actually don't like doing it all that much. Anyway, if you like this video, please do hit like, leave me a comment. If you hated it, leave a dislike, and tell me what you didn't like about it in the comments. Either way, I do hope that you subscribe to the channel, and if possible, please do share this video around, give it to people who you think might like it, and maybe who haven't seen the channel yet. That really helps the channel grow. And if you already are subscribed, please check to see that you have notifications turned on, because sometimes YouTube likes to turn them off. And even when they're on, YouTube is kind of spotty with the notifications. But hey, if you have notifications on, you'll at least usually be notified when I have new content. Anyway, I'm the Dapper Dinosaur. Thanks for watching, but before you go, I just want to say a special thank you to my channel members and my patrons, especially those pledging $20 or above. Work in Progress, Benthoven, Cynically Skeptic, Denny5252, Ian Chen, John Ackerman, Chris Love, Landon Noel, Yapetus, Mabbity Babbity, Sphincter of Doom, The Venerable Bede, and Patrick Dennis. As you probably know, YouTube is a very volatile platform, and from month to month my income on the channel can swing wildly. But the people you see on screen are directly supporting so that I don't have to worry too much about that, and the channel can keep going as it is, and perhaps even improving. If you'd like to join this team, there are links below to join the channel or in the description to join the Patreon. The Patreon starts as low as $1 a month, and the channel memberships start as low as $1.99 a month. On Patreon, you can even get a discount for pledging annually. If you do decide to pledge, you'll get access to an exclusive Discord server just for channel supporters, as well as early access to all of my pre-recorded videos, often up to 2 months in advance. Higher tiers will unlock even better perks. Now, if an annual or monthly pledge isn't right for you, but you still want to support the channel, there is a merch store down in the description, as well as an Amazon wishlist, just for me. And if financial support isn't something you can or want to do, then if you still want to help out the channel, please just like and share these videos and make sure you comment on them. It really helps the channel out. Thanks again for watching.